On-robot Bayesian reinforcement learning for POMDPs. Nguyen, Sammie, Katt, Yuchen, Xiao, Christopher Amato. Abstract. Robot learning is often difficult due to the expense of gathering data. The need for large amounts of data can and should be tackled with effective algorithms and leveraging expert information on robot dynamics. Bayesian reinforcement learning, BRL, thanks to its sample efficiency and ability to exploit prior knowledge, is uniquely positioned as such a solution method. Unfortunately, the application of BRL has been limited due to the difficulties of representing expert knowledge as well as solving the subsequent inference problem. This paper advances BRL for robotics by proposing a specialized framework for physical systems. In particular, we capture this knowledge in a factored representation, then demonstrate the posterior factorizes in a similar shape, and ultimately formalize the model in a Bayesian framework. We then introduce a sample-based online solution method based on Monte-Carlo tree search and particle filtering, specialized to solve the resulting model. This approach can, for example, utilize typical low-level robot simulators and handle uncertainty over unknown dynamics of the environment. We empirically demonstrate its efficiency by performing on-robot learning in 2 human-robot interaction tasks with uncertainty about human behavior, achieving near-optimal performance after only a handful of real-world episodes. Introduction. Mainstream reinforcement learning, RL techniques, are not sample-efficient enough for online applications in physical systems. Long training hours or unguided exploration can wear out or break fragile, expensive robot systems. Instead, the common approach for policy learning in robotics is to use simulators and transfer learned policies to the real hardware, Sim2Real. However, simulators cannot capture the real world exactly. Therefore, additional techniques are required for successful transfers, such as online system identification or domain randomization. These approaches have shown success, but the research question is far from solved, and transfers fail when the Sim2Real gap is large. Moreover, none of these approaches can, in principle, exploit prior expert knowledge, which is useful for faster learning and often exists in most robotics problems. In our view, the ideal approach should learn directly on physical hardware, on robot, while leveraging prior knowledge. Bayesian reinforcement learning, BRL, has great potential for on-robot learning. BRL is sample efficient and provides a principled solution to the exploration-exploitation trade-off by explicitly incorporating uncertainty into the decision-making process. Furthermore, BRL allows expert knowledge to be easily integrated into the learning process as priors, allowing the agent to exploit knowledge it would otherwise have needed many precious samples to learn. Despite its promise, previous attempts at BRL for on-robot learning have been limited, even for the fully observable settings. This can be explained by the scaling issues of BRL methods and the difficulty of representing the complex expert knowledge available in physical systems. In particular, these methods typically assume straightforward priors, such as a single large Dirichlet table or neural networks, but rarely provide tools to tackle more sophisticated applications. This paper presents a Bayesian approach, incorporating expert knowledge for efficient on-robot learning under partial observability. We first identify typical and reasonable assumptions in physical systems, including some inspired by mixed observability Markov decision processes, and translate them to a Bayesian setting. The next step derives the corresponding Bayesian inference problem, showing how the nature of the prior that we discovered shapes the posterior over the unknown quantities of the problem. This leads to the formalization of a Bayes adaptive BA model specialized for robotics systems. Finally, we propose a method for solving this model by specializing Monte-Carlo tree search and particle filtering, which provides an efficient and principled solution to the original learning problem. We empirically demonstrate its efficiency with on-robot learning in 2 human-robot interaction tasks with uncertainty about human behavior, achieving near-optimal performance after only a handful of real-world episodes. 2 related work. Bayesian RL under partial observability involves maintaining a probability distribution over an augmented state, including both the environment dynamics and the environment state, as proposed by the BA-POMDP framework. State-of-the-art BRL methods for partially observable domains have improved on the BA POMDP by incorporating the partially observable Monte-Carlo planning POMCP, an efficient online planner for large POMDPs. While earlier methods are only applicable to small discrete POMDPs or ones with factorizable dynamics, Bayes' adaptive deep dropout RL was introduced to tackle more complex domains. BETA-R leverages the representation power of dropout networks to capture priors, making BRL scalable to larger domains while being considerably more sample efficient than pure RL methods. In this paper, we also use dropout networks to construct parts of a specialized dynamics model, leveraging assumptions about the factored dynamics and full observability of the robot state. On-robot reinforcement learning. Recently, many methods have performed learning directly on physical hardware. Multiple robot workers are used to collect data for online training of a robot arm to open a door autonomously, used human feedback to learn manipulation tasks in 1 to 4 hours. Meanwhile, combined RL and contrastive learning to learn manipulation tasks online from pixels. In addition, used symmetry-aware neural networks to encode domain symmetries to perform online learning manipulation tasks within several hours, while conducted online learning for locomotion tasks on legged robots. Nevertheless, unlike ours, none of these works addresses partially observable domains or employs a Bayesian approach directly to a physical system. Background: partially observable MDP, POMDP. A POMDP is formally defined by the tuple S-A-T-O-R P-S-Neuro, where S, A, Mo are respectively the state, action, and observation spaces, T-Esc-A Tup S, O Esc-A Hafo, and R-S-Har are respectively the transition, observation, and reward functions. P-S-Neuro equals ball S is the prior about the initial state S-Neuro. The goal is to find a sequence of actions to maximize the discounted return defined as EP equals 0 RT with some discount factor 0, 1. An action A taken in state S will result in a state S, sampled from the transition function TASPi equals PSSA. In a POMDP, the agent can only observe O indirectly related to SPi via the observation function O SPi AO. This implies that the agent might need to use the entire action observation history, which grows with the episode length, to act optimally. Alternatively, acting optimally can rely on a belief, posterior probability distribution, B(S) over possible states, where BS denotes the probability that the environment's true state is S. Given a new action A and observation O, a new belief BPi can be calculated as BSPOS.AO, Basha ASTASP BS. Equation 1 indicates that explicitly belief tracking must rely on access to the known dynamics TS-ASPin of the system. When these are unknown, we must turn to learning-based approaches instead. This work adopts the Bayesian perspective. General Bayes adaptive POMDP, GOMDP, BRL assumes that, instead of access to the system's dynamics D, we have a parameterized prior probability distribution on a high level. On a high level, our agent will maintain a belief over the dynamics and the state and pick actions that optimize future return with respect to this belief. Technically, this Bayesian framework constructs a belief POMDP, an augmented POMDP of which the state space and dynamics include parameters that describe the dynamics of the underlying system. Even if the dynamics of the original system are unknown, it is now again possible to plan and track beliefs in the larger POMDP instead. Definition EBA POMDP. Given a dynamics prior FOIC they and a parameter update function U, then a general BA POMDP is a POMDP defined by the tuple ASADORPS with augmented state space STAS equals STAT and prior PS0 equals PS0 Denote David X as the Kronecker delta function, which is 0 everywhere except at A. The update function U determines the augmented dynamics model OS that to OS that A, specified as DD equals POSO A thet USASEO, where PESOA is the dynamics according to a model parameterized by. Since the GBA POMDP is a POMDP, it can be solved through belief tracking and planning. Unfortunately, the state space is very large, and we need to reach for approximation techniques instead, which will be covered next. Algorithm 1 Online Belief Tracking BAOP. Require belief B S step P, action A, and observation O1, empty next belief 2, while size of BP, do 3, S step B. Sample augmented state 4, Thoeth D Hey. Use GBA POMDP dynamics 5. If poor O equals O, then compare with real observation 6, add if have A. 7, and if end while 9, return B. Belief tracking. Belief tracking is approximated with particle filtering, in this case rejection sampling, algorithm 1. Given a current belief B is PS and new action observation pair, AO, rejection sampling repeatedly samples, updates, and rejects particles. In particular, each iteration samples an augmented state from the belief theth. Vote B and proposes a next augmented state using the dynamics S time, think O, thit A. The proposal is accepted and added to the new belief when the simulated observation matches the real observation O equals O and otherwise rejected. The process repeats until we have P particles to represent B. Note that the updated parameters Y are preserved throughout, not reset in between episodes, so that the dynamics are continuously learned through episodes. Online planning. Algorithm 2 shows how partially observable Monte-Carlo planning, POMCP, a Monte-Carlo tree search method, is used for action selection by building a look-ahead tree to evaluate the expected return of each action. The tree is incrementally built through simulations by calling a simulate function ns times, each starting with a sampled augmented state from the current belief, represented by p particles. When the tree is completed, the action with the largest value is selected. At the next time step of action selection, the tree will be discarded and built anew. For more details on modifying POMCP for GBA POMDP, please refer to Algorithm 2 POMCP NSP. Require current belief B equals S step P. Require number of simulations NS. Empty history for I equals 1 NS. Do sample augmented state. Simulate build a tree. Return argmax BQH0B. Greedy action selection C. Bayes adaptive deep dropout RL. The previous section described the GBA POMDP as a recipe that constructs a belief POMDP from a prior THAT0 and parameter update U. BAYDAR is a realization of GBA POMDP that uses dropout neural networks to represent the dynamics. In particular, it assumes that the prior over the dynamics is captured by a parameter set WW, EW can be neural network weights, and chooses the update function to be stochastic gradient descent with dropout, SGD, which can be interpreted as an approximation of Bayesian inference over neural network parameters. Consequently, BADR is a POMDP with augmented state space S equals S is W in dynamics, DOSA equals POSA W WSAOO, U equal W Mismon LSAO W, where LSA SAO W equals log PS OSA is the cross-entropy loss between the predicted and true next state and observation. The parallel state distribution of B initials P is through SD is the product of the given initial POMDP state distribution P send a prior over the dynamics. Bauer parameterizes this prior PD with parameters dub T and O, representing the transition and observation models, respectively. In general, it is unclear how to set network parameters to reflect prior knowledge, so a data-centric approach is taken instead. In particular, we sample POMDPs from the assumed given prior over the dynamics PD, which in turn are used to generate transitions SAS-O with, for example, a random policy. The prior networks WTAN WO are trained using EQ on transitions generated from the simulators. After training, PDIS represented with an ensemble of M parameter sets, TWON. Online adaptation, a solution to Bauer is, as in any GPOMDP, a combination of belief tracking and online planning. After picking an action with POMCP and receiving observation, the agent updates its belief over the POMDP state and its dynamics according to Bauer's dynamics. As a result, the belief over the dynamics parameters WTAN VOR are updated like an EQ. This time, however, uses a single sample with the real observation from the environment. Bayesian inference in robotic systems. The Bayes adaptive models described in the background are powerful in their ability to capture a broad class of problems. In practice, however, we have more intricate prior knowledge than previous literature can capture. For example, we may be confident enough in our understanding of the sensors that there is no need to learn a model of them or have a reliable low-level physics simulator. On the other hand, certain aspects of the real world will be unknown, such as preferences of collaborating humans, and encoding prior knowledge that can be updated during execution over them will be important. This knowledge cannot be expressed with, for example, Bayesian, which assumes a single set of parameters to describe the prior as a distribution. Similarly, most robots come with a reliable low-level physics simulator, which would be unrealistic to try to represent with Dirichlet distributions or even neural networks. In short, there is a need to incorporate mixed and partial prior knowledge from real-world applications to Bayesian methods. Prior knowledge in robotic systems. Typical assumptions include: there is a high-fidelity simulator of the state of the robot. The internal state of the robot is fully observable. Some high-level system behavior is unknown. The model of the sensors is somewhat known. Expert knowledge in robotic tasks typically includes a physical simulator of the robot in which we can simulate actions. Similarly, the internal of the robot state is observable in most systems. What is likely unknown, and over which we may only have a distribution, is some high-level element of the dynamics of the environment in which the robot will be deployed. In this work, this is the human behavior in a human-robot setting. Other assumptions may apply for different applications, but we hope that most classes of assumptions have been covered here and that it will be relatively straightforward to adapt to future requirements. By assuming that part of the dynamics TR, SR, A, S(r) is known and part of the state, or computed from the state through or is fully observable, we only need to learn smaller transition and observation models, blue boxes. We observe that, without loss of generalization, the state can be divided into internal, robot SR, and external, here humans SH parts. S equals SR SH, see Fig 1. Then we denote TR SRA SR as the accurate but low-level simulator in which we can accurately predict the agent's internal state by unrolling a controller. On the other hand, the dynamics of the environment TSASH are unknown before deployment. We make a similar distinction in the observation and divide it into an internal robot or an external human part, or O. We assume that the internal state or can be computed from the state through a given function, or S-core is fully observable. The observation function over the variable O may or may not be given depending on our understanding of the robot's sensors. Factored Bayesian inference. The GBA POMDP does not provide the tools to capture the expert knowledge we discussed above or how to do further inference over. Instead, we derive a more sophisticated framework starting from the assumptions stated above. Priors. For simplicity, let us consider only the state transition model and note that the state space consists of features S equals SR, SH. According to our assumptions, the transition model T can be factorized into each feature. T of ASP equals TRSR ASR to TSASH. Indeed, our prior knowledge is factored this way. P of T equals PTRPH. Specifically, the dynamics over the internal robot state are assumed known, i.e. a physics simulator F, represented with the Kronecker delta distribution P of TR to FTR. Posteriors. In the interest of updating our belief over the dynamics, we consider the shape of the posterior PSAFO. Given the transition SASO equals AS pine O, we first apply Bayes' rule and notice an interesting but crucial property. PR TSSO equals TSSO and a PHTR SASO equals FTR SAS to PHTHS. Equation 5 indicates that the transition functions are independent of each other given the transition TH-SASO. This first implies that the posterior is also factored. Second, as a result, Bayesian inference can be made in separate computations, one for each factor of the prior. In this instance, due to knowing TR, the posterior simplifies to $F TR PH TA SASO, where the last term depends on the prior representation P TH. Formal definition as a specialized Bayesian model. Here we leverage the shape of the posterior derived above to define a Bayesian framework for robotics. In particular, we use the factorization of the posterior computation to construct a model with a factorization of the parameter update rule U, one for each factor. The transition posterior computation, for example, is defined by an update rule for the distribution over the physics simulator and one for the distribution over the human dynamics. The update rule that corresponds to the Kronecker delta function is simply its identity UR SA SPO equals TR. The posterior parameters of the human dynamics depend on the choice of the prior model PH, which in this case will be neural networks DOV-T with the corresponding dropout SGD update rule UDHT SA S'(O) as in EQ4. For example, EQ5 can be rewritten with a factored parameter update rule. EQ5 equals 4 SPO UWHT S SGD SGD of VHT from FO, and we apply the same approach to the observation function. The prior of known components ETR and OR, as discussed before, encoded by Kronecker delta distributions. Priors over other parts of the dynamics, such as the human's dynamics T and observations O, are a design choice, and here are assumed to be represented by some network parameters, THO. Definition formally, the resulting Bayes model is a PMDP with state-space SRHT, WHO, and dynamics. NIDSMRH, or OSR, tool delivery spot to tool reception spot, working step, workroom tool room, tool table, fetch robot, turtlebot, start turtlebot, tool reception spot, tool delivery spot 0, tool delivery spot 1, start, tool room workroom 1, workroom 0, basket. Basket A, ordered tools delivery, OTD, B, speedy tools delivery, STD, working step, fetch robot. 2 human-robot interaction domains are used in our experiments. Experiments. We experiment on 2 human-robot interaction domains in which the agent needs to learn the tool order and working speeds of human collaborators that cannot be directly observed. Fortunately, the robots come with extensive simulators and need not learn this part of the dynamics. However, before deployment, the robots have no idea in what order or how quickly these tools must be delivered. Instead, they have a uniform prior over these unknowns and must learn these factors online. Ordered tools delivery, OTD. A turtlebot must deliver tools to a human in an unknown order to complete an assembly task. Fig. 2a. Turtlebot can carry multiple tools in its basket at once, and the tools are stored in a tool room while the human works in a workroom. Each time the human worker receives a correct tool, he needs a fixed number of time steps to use it before needing another. When a correct tool is delivered, the human's working step increases by 1. State. A state includes the 2D coordinate of turtlebot, the tools currently carried, and the currently needed tool. The coordinates are internal and known to the robot, while the next needed tool is not. Moreover, even though the tools currently carried are known to the robot, we consider it as a component of SH because the tools currently carried cannot be determined just using the previous X-coordinate, tools currently carried, and the action. For instance, with deliver actions, determining the tools currently carried requires extra information, such as whether the human workers are waiting for a tool. Therefore, S equals SRH, where S equals X-coordinate, SH equals tools currently carried, tool needed. Observation. The agent can observe the current room location, the tool it is carrying, and the current working step of the human, which is only observable in the workroom. The location and tools it is carrying are a function of the robot's known internals, e.g., coordinates, whereas the human working step is external, i.e. O equals OR, OH, where OR equals room location, tools carried, OH equals working step. In this experiment, we consider the observation function known a priori, OR-S, room location, tools carried, OS equals working step if room location equals workroom, thigh if room location equals tool room. Actions controllers. The action space consists of 2 types of actions. Get tool I with I 0, 1, T-1 moves turtlebot to a tool reception spot in the tool room where it can receive tool I from a fetch robot that would get the tool from a table. Deliver moves turtlebot to a tool delivery spot in the workroom where the human can take the tool that he needs if it is currently carried by the turtlebot. The navigation and tool pickup transitions are known a priori, SR equals X-coordinate TR SRA, while the human behavior, SH equals tools currently carried, tool needed, THSA, is not. Reward. The agent is rewarded plus 100 for delivering a tool. To encourage the agent to achieve the task as quickly as possible, each time step is given a step reward of -1. The cost of get tool tools depends on the time it takes for fetch to pick and place items and for the turtlebot to navigate. Episode initialization. An episode starts with turtlebot not carrying any tool at the blue spot. All tools are placed on the tool table, and the human begins with the working step equals 0. Speedy tools delivery, STD. In this domain, the turtlebot must deliver tools to 2 human workers, human 0 and human 1, in separate rooms, Fig 2bb. Importantly, given the same tool, one of the workers works faster than the other. The table now holds 2 identical sets of tools, each containing 3 tools, and each human requires 1 set to complete the task. The tool order is the same for both workers and assumed to be known, i.e. tool 0, 1, 2. State. In this domain, the state additionally includes a speed bit, which is 1 if human 0 works faster than human 1 and 0 otherwise. Moreover, the tools needed are now the tools needed by 2 humans, and for the same reason described in OTD, the tools currently carried are unknown, making S equals to SR, SH, where S equals X coordinate, S equal tools currently carried, tool needed, speed bit. Observation. Unlike OTD, the agent additionally can observe the unused tools on the table when it is in the tool room, and W step is the working steps of two humans, only observable in the corresponding workrooms. Adding table to the observation is necessary because there are two identical sets of tools. Consequently, the complete observation is O, where OR equals X room T carry, O W step T table. Like before, we also assume a known observation function. OR S equal X room T carry, OS equals W step T if X room equals work room T table, if X room equals tool room. Action controllers. Similar to OTD, get tool I with I012 will get tool I from the table. However, deliver J with J01 will deliver tools for human J by moving to the delivery spot of the corresponding workroom. Like before, the navigation and tool pickup transition is known SR equals X coord tar A, whereas the human factors ST carry T need B speed. TSA must be learned. Reward. We apply the same reward for a correct tool delivery and use the same cost for get tool I. Apart from a step reward of -1, a step penalty of -30 and -10 are incurred if the faster and the slower human must wait, respectively. These additional rewards are necessary for the agent to learn to prioritize the faster worker. Episode initialization. Like OTD, Turtlebot starts at the blue spot with no tool. The two tool sets are placed on the table, and the two humans begin with W step equals 0, 0. Priors. In OTD, the transition prior assumes a uniform distribution over T possible delivery orders for T tools. Assuming a correct observation model, we represent these priors using T parameter sets, W of T, WHO. To generate training data for training a parameter set, we pair a random tool order with the correct observation model to sample the dynamics. We then use a random policy to interact with the resulting dynamics to generate the data. In STD, we consider a set S consisting of S possible working speeds. Because the speeds are different, one human worker works faster than the other worker, S2 minus S possible different speed combinations are possible. Over these combinations, we assume a uniform transition prior, which is defined using S parameter sets, DDHO. Similar to OTD, to generate training data for training a parameter set, we pair a random speed combination with a correct observation model and the correct tool order to create the dynamics and then use a random policy to interact. Real-world experiments setup. The experiments take place in a rectangular workspace that measures 5.7.0 meters and contains two tables that represent workrooms. Two identical sets of tools are available, each including a clamp, a sandpaper package, and a tape measure. Only one set of tools is used for the OTD task. Experiment scenarios. We perform experiments in two scenarios for each domain, OTD. The number of tools T equals 3, and the correct tool orders are tool 0, 1, 2 and tool 0, 2, 1. STD. The set of possible speeds S equals 10, 20, 30, and the true speeds are 10, 20, and 20, 10. Evaluation metrics. We report the mean discounted return with GA 0.95, averaged over 5 runs. Each run lasts 10 and 20 episodes for OTD and STD respectively. We also visualize the one standard error area around the mean, and then returning later for the third tool. In the third episode, it learns to retrieve one tool at a time and deliver it until all tools have been supplied, which is optimal. In order to see the robot in action, please see our video. STD seems more challenging as the agent needs more episodes to perform well. Specifically, our agent can reach the performance of POMCP within 10 episodes by delivering all tools in the correct order for both tested working speed combinations. The final policy involves taking two tools of the same type, e.g., tool 0, and delivering them one by one, starting with the faster worker and then moving on to the slower worker. This strategy allows the agent to leverage the close distance between the two workrooms. Please see our video for the learned policy. Simulating T, R, SR, A, S, Cut, R. We first build a map of the experiment area and import it to a commonly used simulator of Turtlebot and Gazebo. This simulator then acts as TR, where we can set the 2D coordinate X coord of Turtlebot, send moving actions, and retrieve the next coordinates X coord. Obtaining observations. Tools on table T-table are determined using the RGB image of the tool table taken by Fetch's head camera. The human working steps DOI step are the number of times the minimum depth in the image from Turtlebot's depth camera falls below a certain threshold, indicating that a human is approaching to pick up a tool. The room location X room is determined by comparing X scored with the room's dimensions. During an episode, T-carry is calculated by keeping track of T-table and DOI step. Other implementation details. Get tool I actions of Fetch are pre-recorded using a multi-step process. First, point cloud data from the head camera is projected into an OpenRave environment. Then, the OMPL library is used for motion planning. Fetch and Turtlebot are controlled through a ROS node, which sends observations to a planning node via a ROS service. The planning node, allowed NS=24 simulations, responds with the computed action after about 2.5 seconds of planning. The prior networks implemented in PyTorch are 3-layered with 128 neurons per layer and TON activation function with a dropout rate of 0.1. They are trained for 2,000 epochs using SGD with a learning rate 0.1, then switched to 0.001 for online learning. Non-Bayesian RL comparison in simulation baselines. To further investigate the sample efficiency of our method, we compare it against several non-Bayesian RL baselines in simulation. DRQN is a recurrent version of DeepQ networks and is a classical baseline for POMDPs. RPPO is the recurrent version of proximal policy optimization. Discriminative particle filter RL, DPFRL, is a model-based RL POMDP method that performs reinforcement learning on the features from a differentiable particle filter. Dreamer v2 is a strong model-based agent which alternates between learning a recurrent world model, therefore can tackle POMDPs, and performing RL using imagined data. It outperformed strong model-free baselines such as in the Atari benchmark. Finally, like before, we also include POMCP running on the true POMDP as an upper bound performance, OTD Sim STD Sim Fig. 5. Simulation results against RL baselines. Averaged 5 seeds with shaded 1 standard error. Results. In Fig 5, our method, barely seen in the top left corner, exhibits significantly greater sample efficiency compared to RL baselines in both domains. Additionally, our approach outperforms from the beginning due to leveraging prior information. Specifically, in the OTD domain, Dreamer v2 requires approximately 1,000 episodes to achieve the performance our method attains in just 5 episodes. In the more challenging STD domain, the numbers are 2,500 and 10 respectively. Among baselines, Dreamer v2 performs best in OTD while DRQN performs best in STD. Regardless, these baselines sometimes act suboptimally at the end of the training, see spikes in their learning curves. For instance, in OTD, Dreamer v2 still sometimes outputs a redundant get tool action instead of delivering its current tool to the waiting human. And in STD, DRQN occasionally prioritizes the slower human worker first. In contrast, RPPO exhibits better convergence performance in both domains. Ablation studies in simulation. To ablate our agent, we perform experiments in simulation with the OTD task with 3 tools. Effective factored models. We conducted an experiment where we provided the same initial training for the prior networks, all trained for 2,000 epochs, and compared the proposed approach, ours, with its variants, namely no factorizations used, i.e. the original BAD-R, factored transition model only, trans, and factored observation model only, OBS. Figure 6a indicates that our method and OBS perform best. OBS likely performs well because ORIN OTD is relatively small, resulting in a slight performance improvement when using the factored observation model. Conversely, we anticipate a more substantial performance improvement in domains where OR is a significant component. Using imperfect observation models. Here we investigate how our approach performs against DRQN and Dreamer v2, best RL baselines in section VE, when we do not assume a correct observation model. For this purpose, we add stochasticity while observing the currently carried tool's T-carry, which is now only correctly observable with a probability p-correct to 0.85. However, the data for initially training the prior observation model is obtained with p-correct 0.5. Effective factored models. Imperfect observation model. Ablation studies and outside the box with 3 tools. In this case, it still confirms the sample efficiency superiority of our approach over the baselines. To our knowledge, this work presents the first on-robot Bayesian reinforcement learning method for partially observable scenarios. By employing factored dynamics and mixed observability assumptions, our method can rapidly acquire high-quality behavior in long-horizon, real-world tasks within a minimal number of episodes, outperforming pure reinforcement learning approaches. Although our tasks are relatively simple, the results clearly demonstrate the potential of a Bayesian approach for effective learning directly on physical hardware. One limitation of the approach is a slow inference speed, as the agent needs time to search for the next action. This weakness can be overcome using a reinforcement learning agent to mimic our agent's actions, as previously investigated. We thank Nguyen, Nguyen, Van Tran, and Yunus Terzioglu for helping in the robot experiments. This work is supported by the Army Research Office under award number W911NF12265 and NSF Grant 22479.